And if you're not comfortable with labeling points on the Cartesian plane, then this is a good point to kind of pause on this and go find some exercises. They're very nice games online where you can just practice placing points on the Cartesian plane, reading points, the coordinates of points of the Cartesian plane, because this is going to be critical for the next bit. And this is where we connect this back to graphs, because we kind of, well, functions, because we kind of just went on a rabbit trail there very quickly. So how we translate a function to a graph is, well, one of the ways we can do it is by drawing a little table of inputs and outputs. And typically, we kind of do 5 inputs, and I'm not even going to try and give a philosophical reason for that. It's just because my teacher taught me to do 5 inputs. So you pick any 5 inputs and you figure out, okay, what is the output of the function when I put each of these inputs into the function. So maybe pause the video at this point and see if you can figure out the correct output when my input is -2. What about when my input is -1 and when my input is 0? And then see if your answers compare to mine. Well, how they compare to mine, my goodness. Cool, so there are the answers that I got for each respective input. And how we translate this into a graph is we take each input and output, so each input and its output, we turn that into a point. So the input is my x coordinate and the corresponding output is my y coordinate. So from these 5 input output pairs, we end up with 5 points to plot. And so we go on to our Cartesian plane and we plot them. So the first point, -2 and 0. So we're only moving -2 to the right. We're not moving up or down. So my point is going to be over there. Okay, and also just a disclaimer that my accuracy with this stuff is just so off. Anyway, and then we've got -1 and 3. So moving 1 to the left and then up 3. So that's going to be, okay, 0 and 6, so not moving left or right, just moving up. So that will go over there. Okay, and then 1 and 9, so that's going to go over there. And then finally 2 and 12, so right at the very top of our grid. So I mean, I guess this representation also has limitations, because there's only so much of the graph you can represent. But the interesting thing that we see, and what happens very often, is that you have families of functions whose graphs look the same, or have certain characteristics in common. And what you will have discovered in previous grades is that there's a special kind of function called a linear function, where you're doing very simple operations. You're multiplying your input, or you're dividing your input by a number, and then you're adding or subtracting a number from that, which is effectively what we're doing here, right? So it might look fancy, but really all we're doing is we're saying 3 times x plus 6, right, if we distribute the 3. So this is a linear function, and linear functions are called linear functions because the graphs of those functions always end up being straight lines. So, and this is the pattern we see over here as we go from one input output pair to the other, is that they form a straight line. So there we go. I've just drawn a line connecting the points that I've drawn, and the whole idea of a graph is that it really grows infinitely in both directions. And so the powerful thing about a graph then is that it allows us to see information that it just allows us to easily access information about the function. So for example, we can see that we have a point over here, and the coordinates of that point are -3 and -3, which means that when my input is -3, the output will be -3. And is that true? So -3 plus 2 is -1 times 3 is -3. So the graph has allowed me to read that without needing to do a calculation. And so the important thing to remember about a graph is that it's a collection of input-output pairs.